Welcome to the second introductory video lecture in the compilers course. So this one is called IN2, it's the second in the series. If you haven't seen the IN1 video, which is why you should take a compilers course, please go look at that video first before you go through this one. So I'm going to assume some of the stuff we talked about in that video. The topic of this video is trusting trust. The goal of this series of slides is to provide you with some high-level insight into what we're going to do in the compilers course. In particular, a lot of compilers involves meta-level thinking, and I wanted to emphasize that earlier on in the course so that when you see it later on in the course, you're not surprised by it. So what's a compiler? You've all done programming, so you've all used a compiler before. If you haven't used a compiler before, this is definitely not the right class for you. So what we do is we write a program. So let's say we have a C program. I open a text editor, create a file called hello.c, and I type in my C program here. Type it in. I want to compile it. I send it to a compiler. Let's say I use a compiler like Clang, which is a C compiler, and we call on the command line, let's say we call Clang, and the -o says that I want to produce an output binary called hello, and this is the input. So this is the input, and this is the output. What we get out of it is a binary program called hello, which I can run. So if this dollar is supposed to signify that I'm on a shell, on a terminal of some sort, and I do /hello, which runs hello from the current directory, and it produces an output. What is a program? So a program is nothing but a text file. If I run this command, so this command is file. It takes one input, which is the file name. So I say file hello.c. It tells me that it's a C program text, which it infers from the .c here, and that it's ASCII. If you type in man ASCII on a command line, this will tell you all the information about ASCII. So in particular here it tells you that there are all of these numbers. Each is a decimal number. So it starts from 0, goes up to 127. Each number is assigned a certain character. So each character has a code. If I provide 67, it knows that this number 67 corresponds to the letter C when it's interpreted. So that 67 is interpreted as a ASCII character. Then it results in printing it out on the terminal or on the printer perhaps, or any other device. So one thing you should ask yourself is, why is it 128? So Quine is a program that generates its own code. So we're going to talk a little bit about recursive programs, just because we're going to talk about how a compiler itself is something that needs to be compiled. So when we talk about this meta-level reasoning, it's useful to start with the simple form of meta-level reasoning. So Quine is just a program that generates its own code. So it comes from a very simple kind of reasoning. A program is just a text ASCII file, which we just saw. And we know that in C, in every programming language, there is some function. So in C, it's printf, and it prints out some ASCII text, right? Whatever ASCII text you want. Since a program is just ASCII text, there must be a program that can print out the ASCII text that is itself the source code for a program. I can easily print out some C code. When you have a program that does that, it's called a program generator, because it is generating a text file that itself is a program. To make matters more meta or more recursive, if you have a program generator that generates itself, then we call it a quine. People have tried to imagine this kind of recursion in popular culture. So if you've seen work by M.C. Escher, so this hand is drawing a hand, and this hand itself is drawing the hand that's drawing itself. So there's this infinite loop going on here. And a quine is very similar to this concept, right? It's a program that generates a program, which is, if you run it, generates a program which is itself. Another good book that talks about this kind of recursion or meta-level properties a lot is this book called Gödel, Escher, Bach. So this is the notion of a quine. So let's look at an example. This is an example of a quine in the C programming language. If you Google quines, and you can can find it in almost every programming language. You should be able to write Quine in that programming language. You have a program that looks like that. So that's a program. You compile it. So it runs through the compiler and it produces machine code. And this machine code is the version of this program that is going to run. And what it's going to do, if you examine this program carefully, it's doing this printf. So the printf is actually producing this program itself. So that printf over here is producing this program. This is a program that doesn't take any input. So when you run it, it actually produces an output, which is the program itself. That's why it's called a Quine. And you can take that output and pass it into the compiler again. And what it produces is a new program, which if you run it, produces itself. So let's say I have a compiler like GCC. What does GCC do? Well, it takes a C program like hello.c and then creates an output, which is a binary. So this is the source code. The source code for hello.c is compiled by GCC and produces a binary. You run it, it prints out hello world. What about GCC itself? Surely that binary doesn't come as a binary. Somebody must have written down this compiler. There must be something like a gcc.c. Obviously, it's not going to be a compiler is going to be a complex project, lots of source files. So it's kind of silly to assume that there would be a single C file called gcc.c. But there must be some source code for GCC that is compiled in order to produce the binary GCC. For the sake of simplicity, let's call it gcc.c as a source code for a compiler. You run it through a compiler. You could run it through GCC itself, but you could really run it through any C compiler. So for example, you could use Clang to compile it. The important thing to realize here is that this compiler over here is a binary. It's a binary program that on the system that accepts source files and then produces machine code. And the machine code here would be GCC. So you're passing gcc.c through a compiler, either GCC or Clang, and the output is a compiler, which is GCC. And the runtime is the original diagram we saw, which takes an input program and produces an output, which is the running program, and the output is then goes to runtime here, and which takes some input and produces some output. As you can see, we started with the source code of a compiler, we created a compiler binary, and now the compiler binary can be used in order to compile a bunch of source code. So that's so far so good. Now what does the compiler have to do in order to compile a program? So let's take this very simple program where it has to print hello world, right? It needs to know when it takes a string characters, it needs to know what is the ASCII value of each character. So C1 here is the character H. So C is a strongly typed language. So it knows that H is a character. So C1, it knows the type of this character. So this is the type of C1 is a char. It's a single byte. It's called char. And in ASCII, that value, you could equivalently write it as C1 can be written as 104. So writing it as open quote H close quote is just another way of saying that it has an ASCII value of 104. Those two are equivalent. Similarly, if I look at the second character, C2, it's the character E, which has an ASCII value 101. These are simple single characters here. So every character here corresponds to, so if there is an E here, corresponds to a single character C2. And that single character C2 corresponds to an ASCII value. However, this part of the string over here is interesting because there is a representation of a new line and it's actually two characters there, backslash and n. So if I take this character C13, the 13th character, it's a character, it's quite different. So if you compare this E with this backslash n, you can see that there is a distinct difference. The backslash n has actually two characters, the backslash and the n, but it corresponds to the ASCII value of 10. It needs to know that its ASCII value is 10 so that when it gives that character to the terminal, it creates a new line. So there is this mapping between single characters and ASCII. That's fairly straightforward, but there's also a mapping between multiple characters, in this case backslash and n. So who's doing that? Where does that mapping come from? It has to be in the compiler. So there is some compiler source, we were calling this gcc.c. Somewhere in the C source code for GCC, there has to be something which takes character by character. It takes the next character. It checks if the C is a backslash. So if C is a backslash, then it takes the next character and then it says, oh, is it an N? So it's a backslash N. I'm now going to return this character. So notice that this is of type car, and the type car is something that's just 8 bits, right? So it cannot have the representation of multiple characters. It's basically that single character which is supposed to be a new line. So when you pass it through the compiler, what happens is, so this compiler GCC has to be built, like somebody has to give you that binary, right? So you do apt-get or something on your Linux system, download the binary of a compiler and you pass it through this binary file. In itself doesn't know about backslash n. What it's going to say is backslash n is not a valid character because this is supposed to be an ASCII value. If the compiler doesn't know what to do with these two characters, it's going to say it's not a valid character. Someone has to teach this compiler what backslash n means. Of course, you might say, well, why return these two characters? We know what the backslash n is supposed to mean. It's supposed to mean the ASCII value 10. So why not just return that? And fair enough, that's exactly what you would do. So in gcc.c, in fact, you could use the ASCII value of 10 and return that, and now everything works. It's great. It creates GCC the binary. So it runs through this GCC. If it sees a backslash n, will return the ASCII value 10 and everything works. So when I compile it, I get this new compiler. Now this compiler that I've gotten, so let's say let's call this GCC1, call this GCC2, because it's a compiled version of this source code that we started off with. Notice that GCC2 now knows about this mapping of backslash n mapping to 10. Because of this code over here, GCC2 knows that backslash n corresponds to ASCII 10. So what we can do now, in fact, replace GCC1 with GCC2. We can take GCC1 here and say, well, let me take GCC2 and use that now to compile gcc.c. Now what happens? The compiler source, I can now change my gcc.c to, instead of returning 10 here, I'm going to return backslash n. And I know that it's going to work because gcc2 already knows how to map backslash n to the ASCII character 10. And so now I can get gcc3, which is, these two are now identical, at least with respect to handling of backslash n, right? So it didn't learn anything new. But by replacing the old GCC binary with the new one, we have learned that backslash n maps to ASCII 10. And notice that the source code now doesn't have to refer to 10 anymore. It just needs to refer to backslash n. So notice that what we've done, the main trick here was that the binary, so this is the binary and this is the source. So the binary can actually change, so have more information than the previous binary that it had. This kind of programming is called bootstrapping. So what we're doing is we're taking some information, compiling it into the new binary. Now it has some more information can be used to make our code, in this case, it's used to make our code more readable. So let's look at another example. Now let's see how we can use this bootstrapping idea to do something kind of evil, I guess. So let's look at a program that's quite sensitive, that affects the security of systems. So if you look at login, when you log into your computer, is just another program. What I've done here is take some sample login code from FreeBSD. FreeBSD is a flavor of Unix, and it's on GitHub. It's easy to go to the URL and just search for the login function. So their function here is called do login. It takes a password, pointer to a password called pwd what's in the password. We want to get the password name. And then in the first step is to get the password from the system. So we get the password of the username. Then we check the entered password against the system password. So this check shadow here is going to check the password that you entered against the system password. So it's doing everything right. It looks highly secure. However, if I wanted to get into a system, all I have to do is mess with this source code. So I could say, hey, if my password name is Anoop, then don't really check my password. Just let me log in, right? So whether you have a user Anoop in your system or not, if I could insert this into the operating system source code, then I could type in Anoop and log in to any Unix system anywhere. Obviously, that's not going to work because somebody's going to look at the source code and say, hey, why has Anoop added this if statement into this login function here? He's up to no good. We should get rid of this code. So notice that this, like I said, is just another program. It's just source code. It has to be compiled in order for it to be used somewhere. So this login program has to be compiled. So what if I put the password Trojan? The Trojan is just a way of putting in some malicious code, lets you log in. What if I put this particular if statement inside my compiler? What the compiler is doing, it's compiling code as before. And so let's say that initially there is login.c that comes in and it goes through the compiler. So let's say I managed to insert this in my GCC compiler. It produces machine code, which is a login program. And at runtime, when I run login, it has this if statement over here, which says when I compiled it, inside this login, I've inserted this Trojan. And the Trojan let's say, for example, let's Anoop login without asking for a password. So now this login binary has been compromised. And the reason is because this compiler has been compromised. Now, obviously, this wouldn't work either because GCC is the source code for GCC is available, right? So you can look at the compiler source. It turns out there is, in fact, another way around it. So why don't we take the compiler source? Inside the compiler source, we create a first match that says, am I compiling? So when I'm running GCC, am I actually running GCC on the source code for GCC? If I am, then what I can do is inside the compile function, so the one that's compiling source code, inside that function, I'm going to add the part that was malicious. So basically the compiler inserts the malicious code into the binary. So remember that it's passing through GCC1 and it's producing GCC2. So these two binaries are not the same. So because what's happening is inside this gcc.c, it contains this part here, which says, oh, if I'm compiling, so notice this GCC1 doesn't contain this malicious code, but this one does. So this is like the second version of the source code, which is used to create this binary. So this binary now contains the code that's equivalent to this if statement over here. So this binary over here says, well, if I'm compiling code, so what I can do now is get rid of GCC2 and replace it, get rid of GCC1 and replace it with GCC2. Now what happens? When I pass source code through GCC2, it's going to insert, so essentially what it does, it inserts special code for compiling login.c. And now when it inserts that special code, it's got this malicious code inside it. Now I can go back and I can change this source code back to GCC1 and I'm running it through GCC2, which produces this new binary, this binary over here. This binary contains this malicious code, but the source code here, the gcc.c, the standard compiler code, doesn't need to have it. The binary that we have is a binary that contains all of this logic over here. And so this binary over here is going to insert into the compiler the stuff that looks for login.c and inserts the malicious backdoor Trojan into the code whenever it compiles compiles login. This binary, you don't know what's in the binary just by looking at the source code. So someone might tell you, hey, download this binary for GCC and run it. Look, you can even compile the source code. I'm giving you the source code for the compiler. You can compile it using the binary of this compiler, but you can't really trust that the binary and the source code are actually equivalent, because in this case they are not. So when you get a binary from somewhere that says, oh, here's a new compiler, you have to trust the source from which you're getting the binary for the compiler. So when you do an apt-get, for example, on a Ubuntu system, you're getting a binary for the compiler from a trusted source. Well, so the question is your source actually trustworthy? And has somebody created a version of the binary that contains this malicious code? The only way you can really tell is by cracking open this binary and checking that it in fact is equivalent to the source code, whatever language it's in. Is the binary actually equivalent to the source code? And the one way to do that is by checking whether inside the binary, whether everything that is inside the binary actually corresponds to the source. So like disassembling the binary to see if the source code you get out is equivalent to the source code that you were given as the source code. So even if the code is open source, you still have to trust the binary when you're running a compiler. So this particular idea of the power of compilers and how one can create this kind of two-level of indirection between the binary and the source code comes from this paper, which is called Reflections on Trusting Trust by Ken Thompson, who's famous for working on the Unix operating system and the C programming language, among lots and lots of other things. And this paper is based on the talk he gave when he received the Turing Award.